Okay, hello everyone. Today I'm going to present to you a biofabrication method for the in vitro vascularization of in vitro tissues. First of all, vascularization is still the biggest challenge in tissue engineering. If you want to create significantly sized tissues, you need to have a vascular network from the beginning of the culture which is perfusible, otherwise your cells will die in the construct and they create necrotic cores. For this is normally ensured by a microvascular network. However, until today, it's actually quite challenging to biofabricate these perfusible vascularized networks from the beginning of the culture. So there are several methods like bioprinting, like FDM printing, in-gel printing, or stereolithography, but the problem here is they have a relatively low resolution, so they are not exactly utilizable for microvascularization approaches, and you also need to have perfectly adapted hydrogels which facilitate the cell survival, the printability, and stability during culture all at once. Then there is organ-on-a-chip. In this conference I learned a lot about organ-on-a-chip, so you can basically do everything with it. However, I think you cannot do very significantly sized tissues with that, and also the different cell compartments are often divided by a plastic membrane from the 3D culture, and also in most cases the flow is only guided around the 3D culture and not through it. What I want to talk about today is templating. Templating is basically the prefabrication of 3D printed scaffolds, and these scaffolds can be embedded into hydrogels, into the cell-containing matrix, and dissolved afterwards via a stimulus, for example. This all started with the fabrication of dissolvable scaffolds which are based on carbohydrates, so basically sugars. And it was in 2012 that Jordan Miller and al. First presented this approach, and they 3D printed a sugar glass, added it to a matrix, and then dissolved it to create channels which can be perfused. It was also shown that you can use this sugar approach with laser sintering to create more three-dimensional structures, or even use freeform printing of sugars to create three-dimensional structures. However, in regards to microvascularization, there are still many problems or many challenges. First of all, it's again the resolution of 3D printing, which in most cases is not good enough for microvascularization. But the main problem with these sugar scaffolds is that they actually directly dissolve after you put them into an aqueous matrix. So you can't actually use them as they are, and you have to post-process them, like adding a coating of like a polymer coating. However, if you do this, you again introduce non-dissolvable remnants which act like a barrier between endothelial cells and the matrix cells, for example. And there are other challenges like the hygroscopy, so you cannot store this material actually, and the dissolution might lead to osmotic pressure. So what we were using in this project was thermoresponsive polymers. Thermoresponsive polymers are polymers that change their physical properties with temperature. In this case, we use polymers which have a lower critical solution temperature in water, which means basically if they have a lower critical solution temperature of 25 degrees, above 25 degrees, the polymer does not dissolve in water, as you can see on the right side, but if you decrease the temperature, the polymer dissolves in water. So this can be used as a sacrificial approach. There are two classes of polymer which are mostly known, NiPAM for once, and polyoxazolines. This project we are using polyoxazolines because they are very biocompatible, they have in vivo stealth behavior, you can fine-tune the LCST temperature, and also you can 3D print this polymer. So, and also there are many applications already, like hydrogels for 3D cell culture, nanogels, 3D printing approaches, and also conjugates, where there are even clinical trials already ongoing. So if you want to use this sacrificial property, this lower critical solution temperature for templating, you have to find a polymer which has this temperature in a physiological range. So every polyoxazoline with a propyl side chain is between 20 and 37 degrees, and we decided to use polycyclopropyl oxazoline for this because it has other positive features. So Besides the material, you also need a fabrication method with a high resolution, and we chose melt electrowriting. Melt electrowriting is basically 3D printing, except that there is a distance between the nozzle where the polymer is extruded and the collector plate, and by decreasing, the addition of an electrical field, the fiber is drawn and elongated, and with this technology you can basically print fibers which are down to 1 micrometer thick, and create different kind of scaffold. And in the direct comparison to conventional FDM printing or 3D printing, you can see that the fibers are much smaller in this case. With this technology, you can create several, let's say, forms of art, I would guess, because not everything is functional in a biological sense, but there are many applications already. So in this project, I took the polyoxazolin and used melt electrowriting with it to generate this vasculature-looking form. And as you can see here, melt electrowriting is not a stop-and-go process like 3D printing. It's actually a continuous extrusion process. So you can see on the left side that the fibers are stacked on top of each other or next to each other, which in the beginning does not look like it would make a good vascularization. However, when you introduce this scaffold into a hydrogel or a matrix, you can see that it swells, and the swelling of the nearby fibers leads to the fusion of those fibers. So you actually have this nice bifurcating structure from a bigger mother vessel to smaller daughter vessels. So when you embed this scaffold into a hydrogel and decrease the temperature, you can actually dissolve it, and afterwards perfuse this with a dye, with media. You can add cells into the channels. So during the development of this technology, we created several different designs, which can all be perfused and used for perfusion cell culture. And the good thing about this method is generally compatible with many hydrogel systems, as long as they are physically stable enough. So, for example, it works with methacrylated gelatin, methacrylated collagen, fibrin. However, it does not work with collagen 1 or Matrigel, for example. And also, compared to carbohydrates, to sugars, we have a much longer time frame for the gelation of the gel. So, together with our collaborators from Erlangen, we characterized the endothelium, and as you can see in this video, after 3 days of perfusion culture, we had this fully endothelialized bifurcating channels. And we also did some other analysis methods like stainings or further functional tests. But we also have Robin Dye here, who is presenting a poster tomorrow in the evening. So if you want to know more about the biology behind this, you can go there and talk to her. So the next step was, how can we make these scaffolds easily usable? Because when you put them just like that in a hydrogel, it's not really reproducible. So what we did was SLA print different bioreactors where you can prefixate the scaffolds. And if you want to use them, you just have to add your matrix with your cells on top of them, decrease the temperature, and then you have a direct connection to the generated channel system. So at the moment, there are many projects ongoing. For example, we do microvascularization of a full thickness vascularized skin model together with the Fraunhofer Institute in Würzburg. And this project is actually quite far right now, so we are able to generate these perfusable skin models, and we are actually going to add endothelial cells. We are also working, but this project has just started on a liver model with primary murine hepatocytes, and we also have international cooperations for kidney, heart, or with our Japanese collaborators from Osaka. We are working on seeding SMCs and ECs together, which are first divided by a transient basal membrane, which prevents the overgrowth of the different cell types above each other. We are also using larger structures for unidirectional perfusion to create aortic artery models, And we are also developing these perfusion chambers in the direction of our unidirectional flow to combine them with conventional pumping systems. So the advantages of this method is that we have a perfusible microvascular channel network in hydrogels without any remnants. It's generally compatible with many matrices, hydrogels, and you can basically create and cultivate your 3D tissue in the same device. So it's actually very easy to use for our biological collaborators. However, we also have some challenges here, and these are basically the limitations of melt electrowriting. So with melt electrowriting, you cannot actually print in 3D. It's more or less, let's say, 2.5D, because only flat scaffolds are possible with that. And the printing conditions are quite harsh. You need a very elaborated setup, and because of this, the printing accuracy in many cases is not as good as you can see on this picture below. And also this polyoxazolin is a very brittle material, so even if we are able to print below fibers with diameters below 100 micrometer, they are so brittle that they cannot be handled actually. So what I meant with elaborated setup is that this polymer has a very high melting temperature, above 200 degrees, and if you print it normally, as you can see in the bottom picture, your scaffold will actually not look very nice because the polymer actually solidifies already in the air. So we need a heated collector plate to make it actually possible. But that was the beginning of the idea that we can maybe use this to our advantage to directly print in the air. And here on the right side, you can see my first manual trial with that. And this led to a master thesis of Vincent Meyer, where we tried to vertically print our polymer, which worked out quite nicely. He investigated the influence of different parameters, and what we saw was that the diameter is mostly influenced by the speed during printing, so we are able to even generate vertical structures in a size of 80 micrometers. The next step was to investigate, are we able to put fibers on top of each other in order to generate three-dimensional scaffolds? He showed this with these bridge-like structures, and what we saw was that the fibers actually fuse together. So we can really generate very stable structures. Here you can see these bridge-like structures stacked on top of each other, so they look like a ladder. Additionally, we were able to create more three-dimensional structures here, and even these spiral structures, which are quite hard to do with other 3D printing methods. So we showed that the creation of these complex sacrificial structures is possible. Here in the next slide, when it comes, this is a video which is 5 times faster than the printing process itself, and you can see that we are basically printing 4 pillars and then a plane of another of fibers, which is the basis for the next level. And with this we are able to use the same materials but in a three-dimensional manner. So in this video you can see the same but with the spiral. It's actually quite a sturdy material, as you can see, because this whole spiral is only fitted on this one little fiber below. So with this we basically have the potential to actually try to get three-dimensional vascularization structures. So as before, what we did was to show when we put them into hydrogels, can we dissolve them? Yes. Can we add a dye? Can we add media? This also works out quite nicely. And also we tried some biological testing with cells in the matrix and endothelial cells in the channel. So for the future direction of this project, we want to increase the complexity of the networks, as I said before. We want to test how dense we can go with these printed fibers. And we also want to include Murray's law, which basically means that the mother vessel is bigger than the daughter vessel in a specific ratio. We also want to include the spatial properties of the tissue for the hydrogel by generating adapted bioreactors. And the idea is also to print directly into the bioreactors, which would not be possible with melt electrowriting, but with this technology it is possible. And we want to achieve a unidirectional flow with pumps. With this, I want to end my talk. I want to thank my whole department, my boss, Professor Dr. Jürgen Groll, and all the collaborators. and also the financing opportunities. And thank you for your attention.
Thanks for the talk. That was great. Jordan Miller was on my PhD defense committee, so it's kind of a small world. But I'm wondering, with this polymer, do you have challenges with the biocompatibility, if there's anything left over? And on top of that, could you mention kind of the dissolving process? Do you have problems with smaller channels versus larger channels?
The dissolving actually works pretty nicely if the channels are actually connected to the media reservoir, so this works quite great. But if you do not have a connection on one side, on one media reservoir, it does not work at all. It's then a very slow dissolution process into the gel, and this takes like forever because it's a polymer, and polymers are really big molecules. But if there is more or less an inlet and an outlet, it actually works quite nicely. And polyoxazolines themselves are actually known to be very biocompatible, so we never had any cell death issues with that.
Right, thank you very much for the interesting talk. I think you briefly talked about the compatibility of the hydrogel material with this process. So could you maybe remind or comment on whether it is compatible with common materials like collagen, Matrigel? I think you briefly mentioned, maybe I missed it.
Okay, for this technology, the hydrogel has to be stable or hard enough that the generated channels keep their shape. So, for example, collagen 1 does not work if it's not modified because you always have this shrinking effect, right? And this will also disconnect the hydrogel, the channels from disconnecting parts because of the shrinkage, and also it will shrink down the channels. So, for example, there is a commercial methacrylated collagen 1 which can be used with this system. We actually do this and it works very nicely. Matrigel, I actually never used it before, but I think it's actually not stable.
Okay. Is it like a stiffness level below which there is going to be this shrinkage? Have you investigated that yet?
Not really, but it depends. Most physical gels do not work, except they are very stiff, like agarose, it actually works, or alginate works, but who wants that for cell culture, right?
All right. Thank you very much.
You're welcome.
Hello. Thank you very much for the nice talk. I have a question where I'm wondering, when you print it, you use high temperatures and...
What do I use? Sorry, it's hard to understand.
Okay. When you print, you use high temperatures.
Yes.
And your polymer, the sacrificial polymer, is thermoresponsive. So when you add the gel around it, does it swell, and do you have some effect of this on the resolution of printing?
Okay, the printing itself is made with the polymer in its dry state, so there is no water involved. So it's basically just normal 3D printing. So we do not have any swelling issues there. But after you create the scaffolds and you add them to the hydrogels, you will see that it swells like 25%, I think was it. But this is, in this case, quite good, because with this we can have this fiber fusion and get this nice bifurcation structures.
Thank you.
Yeah, thank you for a nice talk. I just have a question. How do you connect the 3D printed structure then to your chip? I mean, that is a bit the challenging part, right?
So we have these fixation saddle points, more or less, where I put this kind of glue that I make. So, how do I say it? The polymer itself is dissolvable in water. So if you have like a 50% solution or something, 50% solution of the polymer in water, it acts like a glue. So we put the glue on the saddle points, which is the same material as the scaffold, and then we can connect this.
Thank you.
So I think that's the last question, and on this, let's thank Matthias again and all the other speakers of the session.